Today's lesson is all about how we use tangent to estimate gradient. So we're looking at curve graphs, but of course the problem with a curve is that gradient is always changing. If we look at a curve, for example, let's take a happy quadratic. Anywhere you see that curve is going down, then we have a negative gradient. Anywhere we see the curve going up, we have a positive gradient. Right at the bottom, where the curve sort of almost pauses for a moment, we have a zero gradient. But even if we look carefully within this negative zone and within the positive zone, we have different values. Here at the top, we have a steep negative. So maybe it's something like -10, the gradient up here. Whereas down here, as we get closer to zero, you can see that that gradient is flattening off. So here we have a shallow negative. So maybe a gradient something like -0.5. Okay, so it's a much shallower gradient. On the other side, we have a shallow positive. And as we move up the curve, at each point, that gradient is changing till it gets into the steeper values. But we can't just take one number and say, this is the gradient for our curve, like we do for a straight line. For a straight line, we have y equals mx plus c, and the gradient is always the same, and all things are wonderful. It's not quite the same for a curve. Very funky thing that you can do in AS Math, and from 2020 in IG Math a little bit, is that we can use differentiation to calculate the gradient of a curve. But what we're dealing with today is not this idea of calculating gradients. What we're going to deal with today is a little slightly different thing. It's using the tangent to estimate the gradient of a curve. Okay, so when we work with a tangent, what we are doing is estimating the gradient of a curve. And the important thing to remember is, of course, whether we're calculating or estimating, we're always only working with a gradient at a particular point, because we can't get one value, whether it be a calculation or an estimation, that does all the gradients. So we would need to know, what is the gradient here at this point? What is the gradient here at this point? The gradient at this point? The gradient at this point? Each time, we would have to do a different calculation or a different estimation. And the way we're going to do our estimations is, as I've just said, using a tangent. So we need to know what a tangent is. Okay? So a tangent is a line that's going to touch our curve at a point, but not cross it. So it could cross the curve somewhere else, but at the point that we are interested in, that line is not going to cross the curve. It's just going to bump against it gently, meeting just at that precise point that we're interested in. Okay, so what does it mean? If we then had a point with a tangent and it's in a curve, and let's get some more space so we can scribble more. So let's say we have our curve. Let's say we have our point of interest. Now let's say we're adding into this mix a tangent. Let's see if we can actually draw a straight line and get it in the right place. There we go. Beautiful. Beautiful magic of technology. We have a wonderful tangent that is just touching that curve at our pink point. So, what is really cool is that because, let's just label these quickly. So here we have our tangent. Here we have our curves. happily quadratic again, so positive x squared in this case. And here we have our point of interest. This is the point where we want to know the gradient. What is so amazing is that when this tangent hits this curve, right, they've got to touch each other but not cross, which means that for that split second where they touch, they must have the same gradient. So at our point of interest, gradient of curve equals gradient of tangent. So the value of our estimation is actually about the quality of our tangent. If our tangent is absolutely precisely perfect, we would actually get very close to a calculated value for our gradient. But we are not robots, so our tangents are often a bit wobbly. It does help if you draw them with a clear ruler so that you can see through and you can see your curve and you can best judge where to put that tangent. But let's return to this. Now we've got a curve, a tangent, a point of interest. We have the gradient of the curve equaling the gradient of the tangent. And remember, we even drew our tangent with a straight line, which means that our tangent is a straight line. So once you've got that tangent, you can then use it to calculate a gradient. Always remember that if you have a different point of interest, let's say we're interested in this point here, whoops, then we would need a different tangent. So for, let's say, this tangent here would look rather like this. I don't know that I can rotate. Oh, I can. So you can see he's quite a different tangent to the other one that we're working with here. So for every single point on the curve where you want the gradient, you would need a tangent for that point. Once you have your tangent all lined up and you are ready to go, you can then calculate the gradient of your tangent. So first step, so let's put it here. So to estimate gradient of curve at a point. Seems like dots aren't working anymore since they updated this soon. Okay, first thing you're going to do is you're going to draw the tangent. The second thing you're going to do is you're going to identify 2 points on your tangent. For example, we could take this point here and this point here, and we would need the coordinates. So x1, y1, and x2, y2. Does that give you an idea of where we're going? Once we have 2 points on our tangent, we can calculate the gradient because our tangent is a straight line. So we would use our friendly formula, m equals y2 minus y1 over x2 minus x1. And if we've drawn a good tangent for our curve, then our estimation is going to be very good because our calculation for our tangent will match our curve. So highlights of that is, for a curve, our gradient is always changing. We calculate the gradient using differentiation, but we're not working with that today. Today we're working with estimating gradient at a particular point. Okay, so at a particular point, we're going to estimate our gradient by using a tangent. So we go to our point, we draw our tangent, we find 2 points on our tangent, and then we use those to calculate the gradient. Is everybody happy? I've got some past paper questions lined up so we can actually see this in action. Are you ready to move on and actually use these steps? Okay, brilliant. Let us go find our past paper question. So we are using tangents to estimate gradients. We've got a question here. We've got fx equals 3 minus x squared and gx equals 3 to the x. We're not actually going to use this one because what we're doing is we're zooming in just on the tangent piece. So completing the table of values for fx, we took our g of x. So there's only one value. And of course, we take our 0, we put it in here. So 3 minus 0 squared gives us 3, funnily enough. So then we go to our grid and we draw our curve. And I have to admit, I'm going to do this a little bit quicker than usual. Not quite as accurately, but it's going to give us a good idea of what we're working with. So at minus 1.5, we have 2.25. At minus 1, we have 3. At minus 0.5, we have a 3.25. At 0, we have our 3 that we calculated. At 0.5, we have a 2.25. You, of course, would do this very accurately, checking all of these values are precisely plotted. At 1, we have a 1. And at 1.5, we have a minus 0.75. So we need to be able to see a little bit further down. Minus 0.75 about there. Then, of course, you turn your paper so that you're drawing the inside of the curve. And I just get to struggle here on the screen. So your curve will, of course, look less wobbly and far more beautiful than mine. But there we have a curve to work with. So now we are ready to head to our question. It's the whole point of this exercise. By drawing a suitable tangent, find an estimate of the gradient of the graph of y equals fx when x equals 0.5. So remember, we had to find our point. So when x equals 0.5, where are we on our graph? And then they actually tell us, draw a suitable tangent and then estimate the gradient. So x equals 0.5. Here's our x equals 0.5. We're going to go up to our graph and we're going to change color so that things are nice and easy to see. So we want to draw a straight line that just kisses our graph at 0.5. So again, if you have your beautiful see-through ruler, this will be a whole lot easier. But let's pretend, for the sake of this lesson, that that is a beautiful straight line. Now, we have to go to our line and we need to pick 2 points on our line so that we can then calculate for our gradient. So I like to use straightforward points. So if I can get an axis intersection, that's great. So if we look here, we had a 3, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Yes, so this is at y is 3.1, x is 0. So we have 0, 3.1. Then if we look down here, well, x equals 1 is another nice number to deal with. So 1, and when x equals 1, we come across and we see that y equals 1.2. So we've pulled those 2 points off our graph. So now we have to go 0 and 3.1 and 1 and 1.2. And we're going to use our formula. So the gradient of our tangent equals 3.1 minus 1.2, y change, over 0 minus 1, x change. And if we plug that into a calculator, 3.1 minus 1.2 over 0 minus 1, or minus 1, that gives us m equals minus 1.9. So the gradient, where x equals 0.5, because our tangent is kissing our graph at x equals 0.5, is minus 1.9. That is our estimated gradient for the curve, because it is the gradient of the tangent that we drew. So that's what we're doing each time we do one of these questions. And it doesn't matter how weird and wonderful the graph looks, the concept is always the same. So let's have a look at another one. Table shows some values of y equals x plus 1 over x squared when x doesn't equal 0. Okay, so not a bit of an odd one, not something that we've really worked with. The quadratic in the previous example was far more familiar. It doesn't matter because the concepts are still the same. So if we work through and complete the table of values, we get a 3.5, a 1.94, and a 3.11. Okay, so we substituted the values in, we calculated, and now we are ready to plot. Remember, when you've got this gray blocky in the middle, it means that we have two separate pieces for our graph. So now we're going to go in, we're going to draw the graph on our grid. We're going to do the same thing as the last time. I'm not going to be as accurate as you will be in your exam, because the point of this exercise is the tangent calculation, not the drawing of the graph. So minus 2, minus 1.75, minus 1.5, minus 1.06, minus 1 and 0. Minus 0.75 and 1.03, minus 0.5 and 3.5, right up. Then we have our break. So hand inside the curve to draw a nice smooth line just between your points. And now you start to see also why it is so important to draw your curves accurately. Because if you're going to be drawing tangents and calculating gradients, you want to be within the range that they've said is acceptable. So you have to be starting with an accurate graph. Okay, continuing on the second piece of this graph, we have 0.5 all the way up at 4.5. We have 0.75 at 2.53. 1 takes us to 2. 1.5 to 1.94. 2 to 2.25. And 3 all the way up to 3.11. And again, hand inside the curve, nice smooth curve through all of our points. A bit wobbly at the end there. It shouldn't go the other way around. It should be an up curve. Okay, so we have our curve, and we're skipping a few parts of this question all the way down. Actually, we're going to have to draw that better because now I can see where I must draw my tangent. So we need a smooth curve from point to point. And if we go down, by drawing a suitable tangent, of course, find an estimate of the gradient of the curve at the point where x equals 2. So let's change color again so everything is nice and clear. At the point where x equals 2. So x equals 2 here. So we go up to our curve. We take our beautiful clear ruler and we line it up nicely so that we can then draw a straight line that just touches our curve at x equals 2. Okay, so you can see if we actually carried on with this tangent, we would cross the curve down here. But that doesn't matter because we're not worried about it crossing somewhere else. We're worried about it not crossing at our point of interest. Okay, so we have our tangent drawn. Now we need to do that, finding 2 points on our tangent. So again, we have a wonderful axis intersection. So when x equals 0, y equals, and we also have 0.1s on these ones, so 0.1, 0.2, 0.3, 0.3. And up here, well, here on the outside, we have the 3. So x equals 3, y equals, let's take it all the way across. So it's between 3 and 3.1, so 3.05. Now, if you picked different coordinates on this tangent, you would actually get the same answer because it's a straight line. So remember, the gradient is the same wherever you are on that line. So if you don't like my points, you like some other points, go ahead and use them. As long as they fall on this line, we're good to go. We can even have used this one down here, where y is 0 and x equals minus 0.3. Doesn't matter. Okay, so we have 3 and 3.05, and we have 0 and 0.3. And then we need to calculate our gradient of the tangent, because that's how we're going to estimate the gradient of the curve. So m equals 3.05 minus 0.3, y change over x change, 3 minus 0. So we grab our calculators, set up our fraction, 3.05 minus 0.3 divided by 3 minus 0, or just 3, and that gives us m equals 0.916, and then there's 6 is going on forever. That 6 is recurring. So it's 3 decimal places, 3 significant figures, 0.917. Because unless otherwise stated, we always round our answers to 3 significant figures. So 0.917 is our estimate from our dodgy tangent for the gradient of the curve at the point where x equals 2. See if we can get through one more. Because this one, of course, is a graph of a different shape. So here we've got y equals x cubed plus 3x squared minus 2. We have a cubic graph. Our values come out at 2, 0, minus 2, and 2. So drawing the graph on the grid, we have minus 3 is minus 2. Again, you would take the time to draw this beautifully accurately. Minus 2.5, 1.13. We have minus 2 gives us 2. Minus 1.5, 1.38. Minus 1 and 0. Minus 0.5, minus 1.38. 0 and minus 2. 0.5 and minus 1.13. And 1 and 2. All the way back up again. So when we join these two, might help to join half and then flip your paper so that your hand is always inside that curve, so that you can get a nice and accurate curve that goes gently sloping from each point to the next. And back up. So there we have a beautiful reminder of what our cubic graph looks like. And I'm guessing that you can already guess the next question. The next question says, by drawing a suitable tangent, find an estimate of the gradient of the curve at the point where x equals minus 1.75. So you see, they say the same thing over and over again. But by the time you've done a few of these, you won't even need them to tell you by drawing a suitable tangent. If they just said, find an estimate of the gradient of a curve, you know I must draw a tangent. So, where x equals minus 1.75, and you can see this scale is something different on here. Here we're going, every 2 blocks is a 0.1, I believe. So, 0.1, 0.2, 0.4, 0.6, yeah. So, there is our minus 1. So, minus 1.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and 0.75 would then be there. So there is our point of interest. I think I'm going to go cross-eyed. And that's where we would take our beautiful clear ruler and draw a beautiful straight line. And this one is a difficult one that just kisses our graph. Yikes. At that point. Ooh, there we go. And we extend because we want to make it as easy as possible to use and have those options for reading the scale. Now, given the amount of crosses on the scale, let's be really cheeky and let's take it across both axes in this case. Because remember, we can pick any points on this line. So if we pick this point here, we have the point where y is 0 and x is 1, 2, 3, 4, 5, minus 0.6. And this one down here, we would have x is 0, y is, and in this one, the scale is different. Hey, here we're going 0.1s again. 0.1, 2, 3, 4, 5, 6, 7. So minus 0.7. So we take our 2 points, minus 0.6 and 0, and minus 0.7. And we estimate our gradient. Y change, 0 minus 0.7 over x minus 0.6 minus 0. So m equals, set up our fraction. So 0 plus 0.7 on the top and a minus 0.6 on the bottom, giving us an answer of minus 1.17 to 3 significant figures. And that is the estimation of the gradient of the curve. Because at the point of interest, the gradient of the tangent, our beautiful straight line, is a good estimation of the gradient of our curve. I hope you're all happy. If you're not, then have another look at this. Go through everything, because it's really worth understanding how tangents are so very helpful when you're estimating the gradient of curves.